Okay, so now we're getting on to the hands-on section. Had a lot of theory this morning on the D20 and the family and its positioning in the market, but how do we actually use it? How do we write code? And this is the section now as we start introducing the hands-on part of this training. So we are also introducing a slightly new form of hands-on training with the SAM-D20. And when you installed the toolchain this morning, you also would have installed a studio extension, which is actually the smart sensor training for the SAM-D20. And once that is installed, what you will see is when you click a new example project in Atmel Studio, you'll get a list of example projects. And once you click the drop-down list of the 4,500 example projects available here, you'll see a training tab, Atmel Training. And under that, you will see the specific sense training, the smart sensor. So there's two ways of opening the hands-on document. You can either click directly on this offline help here and open the training document, or what we can do is actually create the project, and then we'll create the directory of the training application. Everything gets loaded up in Academy, well, in Atmel Studio, and here is our training document. So there's a couple of things that I'd like to describe and talk about in terms of this training. Firstly, we are making a shift towards more application-based training. The software framework enables the customer to work at an application layer, and so that's the layer that we'd like to focus on enabling the customer to efficiently design. And so in today's application, we can introduce the specific application that we're looking at for the training. So here you can see a smart sensor. In this case, it's mounted on a bicycle, and we are using the sensor, which is light and temperature, to measure the speed of the bicycle and control certain other things like a bicycle light. But how would a light sensor be used to determine the speed of a bicycle? So you can see that it's mounted near the spokes of a wheel. And if we knew the distance between the spokes and the diameter of the wheel, etc., the frequency of the ripple in the light sensor signal would be related to the speed. And so we might get a fairly messy signal from which we would just have to pick out a certain frequency, but that should be possible. Industrializing this into a real sellable, workable product might be an interesting challenge, but this is the application that we're looking at in today's training. Of course, we don't have a bicycle and we don't have spokes here today, so we have fingers. So we will be using our fingers to simulate the spokes of a bicycle on our SAM-D20 Explain Pro, and covering and uncovering the light sensor at probably a frequency of about 4 or 5 hertz. So everything's slowed down a little bit today. Okay, so what do we do with the signal? In a real-world application like this one, we would probably want to do one of two things. We'd send the information to a head unit, which is made, dedicated as like an OEM product to communicate with a specific sensor, or we might want to support a generic mobile phone, which could support a number of interfaces. Maybe USB, maybe we could use Wi-Fi Direct or something like that. But what we're looking at today is just a dedicated head unit where we can use a custom RF protocol. So we'll be using the MAC stack in the Atmel software framework to communicate with just using an RF transceiver external. So we're using the 8086 RF231, which is a 2.4 gigahertz RF transceiver, and associated with the RF stack, which will run on the SAM-D20, we will be able to enable this wireless communication. So the wireless and ASF talking to the analog sensors are the primary technologies which enable this application. And so let's give you a little bit of an overview as well to the process, how the Atmel design or software engineers put together this application. So one of the things that we're noticing is that when we did some surveys of Studio 6 users, and we asked them, what revision and versioning control system do you use? About 20 or 30% of them said that they used SVN, and another 20% said that they used Git, and up to half of them did not even use a reversion or revision control system. Now, the trends that we're seeing in the industry are for increasing software complexity. You know, companies more and more have to outsource software developments, which effectively means that they're working with multi-site teams, quite large software development teams. Communication stacks and protocols or requirements in applications are increasing and increasing, so the size of project code is increasing. And when you start using software frameworks like the Atmel software framework, it increases the size of your code and complexity, and it enables you to do a level of software complexity which you probably couldn't do before. But in the same way, it also requires a more mature software process. So what we are describing here is the software process carried out by the development team who put this project together. And as a customer, you would be free to use any of the other solutions than what we have specifically recommended here, but it is important that you have solutions for many of these aspects. So this application was developed using the integrated development platform, Atmel Studio 6.1. For quick hardware and software prototyping, we used Software Framework 3.8 and the SAMD20 Explain Pro, part of the new family of Explain Pro evaluation and development hardware kits. So then the software developers working on this project used Git, a distributed revision control and source code management system. So it's important that there is an equivalent kind of platform in place. Git works very well. In addition, we used a private GitHub clone as a code management and collaboration solution for project development. Finally, our software development is based on Scrum methodology, an iterative and incremental agile software development framework for managing software projects. We use Jira and CodeHopper for issue tracking and agile project management. So again, not being prescriptive that these are the solutions that are needed, but this is what we use internally. And then quite exciting development as well in how we actually built this document which you'll be working through. We used Doxygen, which is the same tool we use to comment our code to create the ASF documentation. And this document was using an XSL transform to convert into a DocBook open format, which is typically what we use for the Studio Help. But in addition, we used another transform to create it into a PDF. The significance of that is all the code snippets in this document are actually compiled. They built. So in addition, if we have to make any updates to this documentation, and think about this documentation more as project documentation. So an end customer might need to have detailed documentation of their project and their source code. They could put together something like this eventually, where if we do any updates to the code, we just recompile and build the document and everything is up to date again. So that's a little bit of a background of how we put this application together. Let's give you an introduction to some of the basic concepts here. So the clock setup, how are we setting up the clocks for this application? So we're using an 8 megahertz RC oscillator as an input for generic clock 1, and then that in turn clocks the digital frequency loop, multiplied by 6 gives us a output generator of a main clock of 48 megahertz. Another interesting thing to look at is how we manage the different tasks in the application. So we have a very basic task management system here in this enumerator. We have a parameter for each different task that we will run in our application. And here we can have a brief look at the interrupt and scheduling and how we manage the different tasks. So there's an RTC callback which sets a flag based on a certain amount of time elapsed in our application, and that's our scheduler basically running in main just keeps checking for which flags are set and runs the appropriate tasks as necessary. Later on we also configure the RTC running off a separate generic clock. So the internal 32 kilohertz oscillator is used to generate the output for the RTC. That's about all I'm going to say about this application for now. Everything is described in the document. Please ask questions as we walk around, and good luck.